Good afternoon, everybody. Myself, Acharya Vishvendra, and today I'm going to discuss about damped and undamped vibrations. So let's begin with the worksheet. So here is the comparison of undamped, damped, and forced oscillations. So example of undamped oscillation is a block of mass m is attached to a spring and it is oscillating. So in this case, angular frequency is root k by m, and equation of motion is x is equals to a sine omega naught t plus phi. Here a is constant, so amplitude versus time graph is a straight line which is parallel to t axis, and similarly a versus omega is also straight line because amplitude has nothing to do with the frequency. Now the second case is for the damped oscillation. So in damped oscillation there is a damping force which is opposite to the velocity, because of which energy gets dissipated out of the system and finally the oscillations dies out. So in this case the angular frequency is a bit different. It is root of k by m minus b square by 4m square, and the equation corresponding to this motion is x is at sine omega dash t plus phi. Now here at is an exponential function of time and at is equals to a naught e raised to power minus bt by 2m, and it can also be written as a naught e raised to power minus gamma t, where gamma is b by 2m and it is called the damping factor. So if we see the graphical analysis between at and t, so it's exponential decay. Initially it is a naught and finally tends to 0, whereas it is not dependent on omega, so the graph is a constant with respect to omega. The third case comes out to be of forced oscillation. So what we do is that there is a damping force. So to account for the energy loss due to the damping force, we supply a constant, we supply a force given by f naught cos omega t plus phi. No, phi, let's suppose that. So initially the system is a bit turbulent, but finally the system oscillates with the frequency of the driving force, which is omega. And the equation of the position is x is a dash sine omega t plus phi dash. Here a dash is the amplitude which is dependent on omega in this particular case, and a dash is f naught by omega divided by root under omega square minus omega naught square whole square plus b omega by m whole square. This is the amplitude in case of forced oscillation. We can say that it is independent of time, but certainly it's a function of omega, and at omega is equal to omega naught the amplitude is maximum. This process is called resonance, and at that frequency amplitude of oscillation is maximum. So resonance find its use in many practical applications, like all the receiving and transmitting signals, they works on the basis of resonance. Radio signals, they works on the basis of resonance. So it's that when frequency of the external driving force is equal to the natural frequency of oscillation, the amplitude tends to be maximum, and this magnitude is given by f naught by b omega.